Hi, everybody. Welcome to this session, OD31, Understanding the Cryptographic Controls in Azure SQL Database. My name is Michael Howard, and this is one of my favorite topics amongst all the other favorite security topics, but this is definitely like number one, maybe, along with all the other ones. Anyway, let's get stuck into it. So the core objectives here, I'm not going to do an agenda. I'm not big on agendas, just objectives. Like, what do you want to learn out of this thing? So the first one is I really want to think about some structure when you're talking about security controls. It's like, where do we use them and why do we use them and how do we think about them more from a structural perspective as opposed to sort of like picking a security technology, throwing it against the wall and see if it sticks. And then finally, we're going to learn, the most important part, right, is why you're here, is to learn some of the subtle nuances of those cryptographic controls that are built into Azure SQL Database. So I really want to start off with something that I've been talking about for a long time. That's this big lie. Security is only as strong as the weakest link. Not true. Never been true. Not true. Won't be true. Because cryptographic controls are so good when they're done correctly, right? There's a last line of defense when all else fails. They're a fantastic last line of defense because the data is protected both from disclosure through encryption or tampering, say through a MAC, an HMAC, which is a message authentication code or perhaps a digital signature. There's all different ways of protecting that data. So it all boils down to like protecting the keys at that point. But as a last line of defense, cryptographic controls are magnificent. And this is one of the reasons why controls like this are often referred to as compensating controls, because they're there to compensate for weaknesses elsewhere in the environment. And this is also really important when you're looking at zero trust assume breach, right? So assume breach, the system is completely destroyed. What other controls do we have that come into play? And again, well-designed cryptographic controls are a magnificent last line of defense when the whole system is completely destroyed. Now, before I sort of move into the features in SQL, I really want to just give you an idea of the different controls that you have at your disposal, and most importantly, I provide a little bit of structure when it comes to thinking about those controls. And there really is this cryptographic quadrant of the various controls, and there's symmetric ways you can do that. So symmetric is where both parties, all communicating parties, share the same key. And then there's asymmetric ways of doing it where there's a public key and a private key. Then there's two different broad mitigations you want to achieve: confidentiality, and the second one is integrity and authenticity or authentication. And from a symmetric perspective, the most common algorithm here today is AES. There are other ones as well, but by far the most common one is AES. Another one that's becoming popular is Cha-Cha, which is derived from an algorithm called Salsa. Yeah. But that's becoming popular as well. And then for integrity and authentication, there's like SHA-2, SHA-3. SHA-3 is new, so SHA-2 is still being used predominantly. And then you have things called HMACs. So that stands for a hashed message authentication code. Best way of thinking of it is like a hash function, but with a secret as well. And then the asymmetric ways of doing confidentiality primarily is RSA, which is a very, very well-known public key cipher. And then for integrity and for authentication, you have the digital signature versions of RSA and elliptic curves. So again, I'm not going to go into all these in any detail, but when you're thinking about the cryptographic controls that you want to use, this is like the quadrant you need to think about. Next one is when you're thinking about security controls, you've got to think about what you're actually trying to achieve, like authentication, authorization, audit. You can read these as well as I can. And then where they actually come into effect, like at the control plane or the data plane. So the control plane is administration of the environment, and the data plane is actually the day-to-day usage of the environment. We're going to focus just on three, which are cryptography at rest, cryptography on the wire, and then finally cryptography in use. So let's focus first and foremost on cryptography on the wire, which is TLS. It's basically just TLS. I mean, yes, you could use SSH, secure shell, but honestly, I've yet to come across an implementation, or not implementation, but a deployment of SSH that's actually been secure. That's a whole discussion for another day. So TLS is always the preferred way of doing sort of cryptography on the wire. The quality, what's often referred to as quality of security services that are offered by TLS, there's 4 of them. 3 are there by default, and the 4th is optional. So the first one is server authentication. This is the most important step, by far the most important step. You've got to authenticate the server first. Because if you don't know who you're talking to, what's the point of having a secure channel? Because you don't know who you're talking to, so what's the point? So server authentication is so incredibly important. And this uses X.509 version 3 certificates today and an associated private key. So the public key is in the certificate. Next one is channel encryption. That's usually done using AES, although there are some versions that use this algorithm called Cha-Cha, but the most common one is AES by a long shot. And then integrity controls, so for example, an HMAC SHA-256. And then the last one, which is optional, is client authentication. So it is actually possible for the client to actually say, okay, I want to authenticate myself using a certificate as well. So the prime example there is a smart card, right? So the smart card will actually have the certificate or certificates and a private key, and it's actually stored in silicon, right? So you put the smart card in the reader, and then as part of the TLS handshake, it can actually authenticate the client to the server. That's optional. The first three are basically not optional. The fourth one is. So the client authentication part is optional. When you're connecting from a client to SQL Server, you got a connection string, right? We all know connection strings. The two you need to worry about are encrypt and trust server certificate. I don't like encrypt. I think it's the wrong term. If I had my way, I would change it, but it's not going to change. Because it's not really encryption. It's not just encryption, I should say. It's encryption and tamper detection. If I had my way, I would change that to say, I don't know, protect or protect channel, because that's way more accurate. The one that is also really important here is trust server certificate. If you have trust server certificate equals true, that is a euphemism for connect to absolutely anything in the world because there's no server authentication going on. Sounds cynical, but that's kind of a waste of time. So trust server certificate equals true is really not a good idea. Trust server certificate equals false doesn't mean we don't trust the server certificate. What it means is verify that the certificate is correct. If I had my way, I would change that to verify. So trust server certificate equals verify will be much more accurate term there. But it goes through all the correct certificate checks, right? So chaining up to a trusted root, like it's been issued by someone you know and trust. Make sure date ranges are correct. Make sure things like extended key usage says server certificates. Perhaps even making sure that the certificate's not been revoked. There's a whole bunch of checks. Make sure the signature is correct on the certificate. All those good security checks. So these two here are the recommended two settings, minimum. Encrypt equals true and trust server certificate equals false. And then actually go through and make sure the client's doing all the appropriate client-side certificate checks. For SQL Server 2022, we added a new option to encrypt, which is strict. That totally disables trust server certificate, which is good in my books. And basically what it will do is a full certificate check to make sure everything is correct from a cryptographic perspective, including the name is correct as well. And then it also will support TLS 1.3. And essentially what we did in SQL Server 2022 is we broke apart TDS from TLS. So historically, the two were sort of intermingled. Those have now been broken apart, which is magnificent. It means that we can upgrade protocol versions, the TLS versions, without having to change the underlying TDS work, which is great. So kind of how TLS works, there's a whole bunch of steps that go on. I don't really want to spend too much time on this, but it's really important to understand kind of at least a somewhat low level, kind of what's going on. So first and foremost, the client and the server agree on a protocol version. Like we're going to do TLS 1.2 and there's Cipher Suite. I'll talk about Cipher Suites in a minute. The client then authenticates the server by using the server certificate and private key. Remember that actually the client doesn't have the private key, right? The private key stays on the server, but the private key is used indirectly by the client through the public key to verify that it's actually that server. Optionally, the client can also authenticate the client, right? So the server can authenticate the client, which we already just mentioned. Then there's either a key exchange or key agreement, depending on the protocol that's being used. And then after that, the data is encrypted using the agreed upon what's called the Cipher Suite, or the actual set of low-level crypto primitives that are used to encrypt the payloads on the wire. The first step is, in the overall scheme of things, relatively expensive. It really isn't that expensive, but relative to bulk encryption of the data, yeah, it is definitely more expensive. That being said, elliptic curve certificates that use elliptic curve for all the key exchange and so on, or key agreement if they're using what's called Diffie-Hellman underneath that, that is much more efficient than RSA. So that's why if you're using elliptic curve rather than RSA, it's much faster. And that time overhead, that first block, those first sort of 4 bullet points, it's not a big a deal compared to RSA. But once that session is established, it's really, really high speed, right? Because AES, if you're using AES and say an HMAC SHA-256 are actually really efficient and very, very fast. So when it comes to negotiating security between the client and the server, they must agree upon a mutually agreed upon cipher suite. I'll talk about cipher suites in the next slide. If there is no agreement, there is no communication. End of story. So if the server says, I will support these cipher suites, and the client says, I support, these other cipher suites that have nothing in common with the server's cipher suites, there is no communication. Now, I really want to stress something that's incredibly important here, and that is that the server always decides. The client does not. We don't trust the client. The server always decides the protocol version and the cipher suite. So if the server says, I only do TLS 1.3 and 1.2, and the client says, I'm going to try a rollback attack, right? Because I know there's a vulnerability in TLS 1.0. So I'm going to use TLS 1.0. Go ahead. The server is going to reject the request. So the server always decides. Don't try configuring a client to try to get around some setting at the server. It's not going to happen. So the server always decides. And a cipher suite is really just a set of crypto primitives that are used to do all these things like key exchange or key agreement, encryption, and integrity checking. And the way it works is a server, and a client for that matter, will have an ordered list in descending preference. So they may have, say, I don't know, let's pick a number, 10 different cipher suites. And the top 1 and 2 may be the ones that you really prefer. And then you get down to the bottom. And they usually, often the ones at the very, very bottom are there for backward compatibility reasons. But the server may actually have a really strict and very small set of cipher suites that it supports. And that list of cipher suites is really important. You've got to keep it as small as possible. So what does a cipher suite look like? Well, here's an example of one. And I do realize it looks like someone sneezed on the screen, but this is what a cipher suite looks like. So the first part, TLS, means this is a cipher suite that's supported by TLS, so not SSL, right? There are cipher suites that are supported by SSL. You should never use SSL. Never. It is gone. The letters S, and L should never pass your lips. So this is for TLS only. The key exchange, this is key exchange, we use RSA. And then for bulk encryption, for the actual encryption, we use, here we're going to use AES 256, so 256-bit key, using cipher block chaining, right? So that's the actual encryption mode. There's all different ways of doing it. Another very common one is what's called GCM, which is Galois counter mode. And then finally, we're going to use a SHA-256. It's actually an HMAC. So it's a hashed message authentication code. And the fundamental primitive that's used there is SHA-256. And there's a whole bunch of them, right? There's a whole bunch of them. And again, you'll have a list of these in preferred order. So that's TLS, right? That is for cryptographic controls on the wire. And it is by far the most common of all the cryptographic controls, by far. And that will give you, remember, it will give you server authentication, channel protection, so encryption and integrity control, and then optionally client authentication as well. So now let's turn our attention to cryptography at rest. So the major technology that we use for encryption of data at rest is transparent data encryption. It's been around for a long time, long time. Very easy to use, no code changes required. You literally just click on a button and that's it. In the case of Azure SQL Database, the only real option you have is to choose either customer managed key or platform managed key. Some customers require, usually for compliance reasons, that they actually control the whole key lifecycle, which means they must use customer managed keys. The downside of that, and this is really important, is we don't have a copy of the key, right? Or the root keys. We don't. We being Azure. So if you lose the key, there's nothing. You can't go calling support and get the key back. That's why Key Vault has like purge policies enabled and sort of soft delete policies enabled for that exact reason. And so if one is actually either accidentally or maliciously deleted, the key sort of hangs around, even though it's not usable, for 30 days. That way you can sort of, bring it back in the case of an accident or even malicious deletion. This is designed to mitigate disclosure of like a stolen device, a stolen hard drive, or even a stolen machine for that matter. But it also encrypts backups. This is really important because the backup, if it's stored, away somewhere, perhaps on-prem or in a storage account somewhere, the key is nowhere to be found. It's not even close to the backup, and the backup must be brought back into the SQL instance to be restored, which is where it will then have access to the keying material. It is highly recommended that the root key be stored in Azure Key Vault, because then you get all the benefits of Key Vault, like access control and auditing, and frankly, Defender for Key Vault. And that includes SQL Server inside of a VM. You can actually store the root keys that are used to protect this hierarchy in Key Vault. So we have a whole bunch of new features in TDE, in Transparent Data Encryption. The first one, which is actually something I'm really excited about, is automatic key encryption key rotation, often referred to as the protector key in SQL parlance. This is actually a Key Vault feature. A lot of other technologies in Azure use it. So, for example, storage accounts can use it as well. But this allows you to, say, rotate the keys automatically on a one-year basis, for example, or, every 30 minutes. No, you shouldn't do that. But the point is you can change it on a regular basis. Next one is user-assigned managed identities for accessing the TDE keys using custom managed keys. Historically, we only supported system-assigned managed identities, but now we support user-assigned. And then another feature which I'm really excited to see, it's in preview, is per database custom managed keys. So historically, if you had a server and you had like 20 databases, just made that number up, they would all be encrypted with the same key hierarchy. Well, now you can actually have separate keys per database, and it provides a really nice level of crypto isolation between databases, which is nice to see. So that's by far the most common way of encrypting data at rest in SQL Server and Azure SQL Database. Next one, which is kind of a new category, is cryptographic controls for data in use, like actually providing cryptographic controls while the data is being used. And the technology that we have there is called Always Encrypted. So you really have this spectrum of things, right? So on the left-hand side, you have, just think about it, right? So databases are designed to query data, right? That's why they exist. I mean, sure, you can insert, you can update, you can delete, yep. But a big part is querying the data. On the right-hand side, we have a real problem here, because if we want to encrypt the data, the whole point of encryption is to prevent querying the data. That's the whole point. So we've got a real problem, right? We've got data that, database is designed to query, and crypto or encryption is designed to prevent that. What's amazing here is Always Encrypted meets you in the middle. So, if anyone who knows me, I'm incredibly pedantic with my wording when it comes to crypto controls. So I'm going to read this very, very carefully and follow along with me. I really need like one of those little bouncing balls going across the top. Always Encrypted allows you to perform some queries. Actually goes beyond queries, to be honest with you. You can do inserts as well and updates, but this is all about querying. Allows you to perform some queries, not absolutely everything, over encrypted data without decrypting the data. It's kind of cool. Without decrypting it at the server. And this is really important because SQL Server does not have the keys. It doesn't. So in the case of, complete server compromise, the attacker only gets ciphertext. They don't get the plain text. And in fact, they can't go looking for the keys in the SQL Server process because they're not there. They're just not there. Now, I realize you're probably thinking to yourself, man, this sounds like magic. It's actually very, very simple and incredibly elegant. And I'll talk about it as we go through this in a bit more detail. So Always Encrypted encrypts, and decrypts, obviously, and HMAX column data. This is the key part. The data is actually encrypted and decrypted by the client SQL Server driver. So ODBC, OLEDBC, JDBC, whatever. It is all, that crypto is done by the driver. It is transparent to your application. What's important here is that it is never encrypted and decrypted at SQL Server. Like the actual SQL Server process does not do any of this crypto work. It doesn't. It's all done at the client. And the data is only stored as ciphertext in SQL Server. Only. Now, I'm going to get really pedantic with some words as I move through this because there's a really subtle nuance here when we're talking about what are called enclaves, which I'll talk about. I also want to point out that Always Encrypted is not SQL Server column encryption. They are completely different beasts. SQL Server column encryption has been around for a long, long, long time, and you really shouldn't be using it. I'm not going to say it's of no value, but the point is that the keys are in memory, in the SQL Server process memory. And also it can be a bit of a load on the SQL Server process. So Always Encrypted is not the same as SQL Server column encryption. They are completely unrelated technologies. As I mentioned before, SQL Server does not have the keys. It doesn't have the keys at all. And the algorithm that it uses, or the cipher suite that it uses, is down the bottom there. I'll go through that in more detail in a couple of slides. With Always Encrypted, there are two flavors. there is a version that uses secure enclaves, and there's a version that doesn't use secure enclaves. Cosmos DB today actually supports the non-enclave version of Always Encrypted as well. So here's what Always Encrypted without enclaves looks like. So sort of bear with me here as I walk through the process. So if you've got some sensitive data, let's say you've got a column, say a social security number, which really should be national identity number, by the way, and that sounds cynical, but let's be real. So when the client code wants to insert, say, a new row, and part of that is the social security column, that cell, the row column, will actually be encrypted by the driver, not by your code, but by the driver. So when you do insert blah, 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 social security number equals blah, 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 that column is automatically encrypted by the driver. And then there's then sent up to the server where it is then stored. What's interesting here is that that's all done transparently. It's all, I'm not going to say automagic, but it kind of is automagic. It's all done by the driver. And the data is stored in SQL Server in an encrypted form. When you do a SQL query, so select star from customer where social security number equals blah, that social security number is actually encrypted at the client, sent up to the server. The server does not have the keys. All it has is the ciphertext, because that's all the driver gave to it, right? It was just the ciphertext. So then what it does is it can do an equality operation on the two sets of ciphertext, the two sets of encrypted social security numbers. And if they match, that is sent back to the client, encrypted, and then the client decrypts it and then displays the social security number on the screen, assuming that's what you want to do. This is really, really cool, but it's only for equality and inequality, equals and not equals. That's it. You can't do like greater than or less than with this environment, but it works incredibly well for what it does. The next version is with enclaves, and there are two versions of secure enclaves. There's SGX enclaves and VBS. So SGX stands for Software Guard Extensions, and this is a feature of certain Intel CPUs. So if you decide to use this and you want to use specific kind of when you're selecting like the compute layer underneath you've got the option of actually using this, which means that we will actually set your instance up on an image that actually has access to these CPUs. The other option is VBS, which is in preview right now, stands for virtualization-based security. And the isolation actually comes from the hypervisor. So the same technology that we use to isolate one VM from another is the exact same technology. Now, essentially what we do is we load a part of the query engine into the enclave. And the enclave is completely isolated memory. If you actually compromise a SQL server and try to see where the memory is for the enclave, it doesn't exist. It doesn't exist at all. The nice thing about VBS enclaves is that there's more compute options than SGX enclaves, and more region options as well. So even though it's in preview, it has much more flexibility than the SGX enclaves, and frankly, it's a lot easier to set up as well. That's a whole nother discussion about attestation, which I don't want to get into right now. That could be a presentation unto itself. So the way it works is somewhat similar to the non-enclave version. So you do insert blah, 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 social security number, blah, 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 blah. That is encrypted at the client, and the client must have access to the keys, obviously. So that could be stored in Key Vault as an example. So let's say you insert the data, that's encrypted, and then it's just inserted in an encrypted manner into the database. Then let's say you do a select star from customer where social security number is like something. That query is sent to SQL, and it is then passed off to the enclave. The enclave decrypts it, so now it knows what the like statement really looks like. It will actually perform the query over the plain text, and then it will send the resulting ciphertext back to the client, where it's then decrypted. So the enclave does have access to the keys. It does. But what's important is that enclave is not SQL Server memory. It's not. Whether it's SGX or VBS, it is not SQL Server memory. So if SQL Server is completely compromised, the keys are not there, and the plain text is not there. The best you're going to get is ciphertext. So this is a really, really important extension to Always Encrypted, because of this very fact that the ciphertext, basically the ciphertext absolutely everywhere, except in the enclave. And obviously at some point between the SQL driver, like your I don't know, system.data driver or ODB driver or DBC driver, then it's decrypted automatically and then presented to the client. Authorization policies aside, of course. But what's really nice here is you can actually take some data in, say, in plain text, and you can do encryption of that data, bulk encryption of that data, without moving the data out of the database. And this is because the encryption and decryption is done in the enclave. So again, I really want to stress here, the only time the sensitive data is actually in plain text is between the driver, the SQL driver, and your application, which is basically the same process, or inside the enclave. Everywhere else, it's just ciphertext. This is a magnificent, magnificent technology. If you have current code, you will need to redesign the code, to work with Always Encrypted. It's just a simple fact of life. I may as well just pull the Band-Aid off now and just tell you. You can't just flip Always Encrypted and just say, go ahead and work, because it's not going to work. Your SQL statements will fail. However, if you're designing a system from the ground up, you got like a greenfield application, absolutely. You should really be considering Always Encrypted from the design, from the outset. As I touched on it before, SQL Server does not have the keys. It doesn't. They're not there. It's plausible deniability, right? They're not there. And if you do not have an enclave, then that encryption and decryption is done in the enclave. It's not done in the SQL Server process. There are two versions of Always Encrypted, not going beyond the enclaves, and that is deterministic and randomized. Basically, deterministic is mainly used with the non-enclave version primarily, and we have to do that, and you'll see why in the next slide. Deterministic basically means that, and I realize I'm getting into sort of crypto dreamland here, but the initialization vector is the same. Whereas with randomized, the initialization vector is different all the time. The nice thing is that secure enclaves will work with randomized data, whereas the non-enclave version can only really work when you're doing a query against deterministic encryption. So here's an example of, I've just taken a dump of a small table that is using Always Encrypted, but I'm not decrypting the data. So this is what an attacker would see. And you'll see that everything is, basically absolutely everything is encrypted. That's just a hex encoding of the ciphertext. So there's nothing there to see. There's no keys to look at. There's no keys in memory. If I compromise the memory, I can't get the keys. So this is great to see. You'll notice, if you look carefully, you'll notice that that first byte is always a 1, always. And the reason for this is because this is CipherSuite version 1. And that's what the CipherSuite is down the bottom. And actually in the next slide, I'll explain what this CipherSuite actually means. Well, let's say there's a vulnerability found with that combination, and it's really, really bad. Well, we could actually invent a version 2 that uses something different. And that means that for old versions, which are version 1, we could always read them, right, using this CipherSuite, and then write them back, but write the first byte as a 2, assuming we're updating to a new version. And then that way we would know that's using a different CipherSuite. So we could actually read and write, different protocol versions without breaking the application. And that's referred to as crypto agility. That is a whole nother presentation. Crypto agility is like easily another 30, 45, 60 minutes, depending on how many stories I tell, session unto itself. Big fan of crypto agility. So version 1 is that CipherSuite down there. Let me explain. By the way, actually, before I jump onto that, look really, really carefully. If you look really carefully, look at row 5 and row 11. You'll notice that row 5 is Gollum and row 11 is Smeagol. Now, for those of you who know, Gollum and Smeagol are actually the same person. And if you look really carefully, you'll notice that the ciphertext for the social security number is exactly the same. It starts 01, well, surprise, surprise, that's the version number. Then F5C4CA. They're both the same. We're using deterministic encryption here. So they always give the same ciphertext. And this probably an indicator that we're using the non-enclave version of Always Encrypted. But that's how so you could do, say, select star from, I don't know, characters where social security number equals blah, 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 blah. And if that's the social security number for Gollum, you'll see it'll bring back Gollum and Smeagol. If that was using randomized encryption, or using always encrypted with secure enclaves, we wouldn't see that these two cells were actually the same. All I know from looking at this is that Gollum and Smeagol have the same social security number. I don't know what it is, but they have the same social security number. But with randomized encryption, you wouldn't have that. But at that point, you can't use the non-enclave version of always encrypted. I hope that makes sense. So let me explain really quickly the cipher suite itself. So the very beginning there, that AEAD stands for authenticated encryption with associated data. I'll explain that in the next slide. Then we're using AES-256 with cipher block chaining for bulk encryption. And then we're using an HMAC SHA-256 for the integrity protection of the data itself. So the AE part of AEAD stands for authenticated encryption and that is used to bulk encrypt and protect, in this example, the social security numbers. AD stands for additional data. This is data that is MAC'd for integrity control, but it's not encrypted. Because if you think about it, we can't encrypt the version number nor the initialization vector. We can't encrypt either of those two things because we need both the version number to know what cipher suites to use and the initialization vector to go into the bulk encryption algorithm. So they can't be encrypted, but we do want to protect them. And so we protect them with an HMAC, and that prevents them from being tampered with. They're not encrypted, but they are HMAC'd. And that's exactly what AEAD actually does. Now, for grins and giggles, if you really want to know how this stuff works, go and look at the source code. Think about it for a minute. The SQL data client actually has this built into it. It has to have it built into it. So you can actually go to referencesource.microsoft.com and actually look up the class that actually does all this work. You can actually see things like the version number being put in there, where the initialization vector comes from, and how it's calculated, so on, and how the encryption is being done, so on and so forth. Now, there is one little thing that Always Encrypted does not protect against. Always Encrypted is designed to mitigate tampering within the cell. So if I go and change a byte in a cell, like one intersection of a column and a row, it won't work, right? Always Encrypted will actually detect. The HMAC won't work. But what you can do, in theory, RBAC controls aside, you could actually potentially take one cell and paste it into another cell without even knowing what the ciphertext is. You could potentially do that. Again, RBAC policies aside, that's why you still got to have strong RBAC policies, right? Or roles and permissions on SQL. So how do we mitigate that? Well, we actually have a technology that can do that, and that's Ledger, which is built into Azure SQL Database and SQL Server 2022. And this mitigates tampering, like what I just showed, by a rogue admin, even an admin with cryptographic key access, and there's a reason for that. This builds on temporal tables, which have been a SQL Server feature for quite some time now. And essentially what it does is it hashes data. On an ongoing basis, it hashes data. And we build up a thing called a Merkle tree. And a Merkle tree is just a hierarchical tree of hashes. The reason why we do that is because it's more efficient when you're searching, when you want to verify that a ledger, data's been tampered with or not. Now, here's the really important part. I really want to stress this. This is the absolute linchpin of the cornerstone of the foundation of Ledger. That resulting Merkle tree must be stored in a tamper-proof service. You could store it in a storage account with a strong RBAC policy, but a rogue admin can still go in and change the RBAC policy and change the data. You need to store it in something like either Azure Immutable Blob Storage or Azure Confidential Ledger. Azure Confidential Ledger is not the same as SQL Ledger, but you could store it in either of those two services. The most common one by far is immutable storage. So immutable storage is basically you can't touch the data. When I mean touch, I mean you can't change the data. You can do reads, but you can't do writes or updates. You just can't, or deletes. You can't do it. And there's two versions of immutable storage. The first one is time-based. This is the recommended way of storing ledger data. It's basically saying that data in there can't be touched for, say, 180 days. Can't be touched. You can phone up support and tell them, hey, I made a mistake. I need to change that to 90 days. It's not that support can't do it. It's not that support won't do it. They actually can't do it. And by can't, I don't mean through policy. I mean the APIs are not there. We actually turn the APIs off. The only way you can actually delete the immutable storage is actually to delete the subscription. And honestly, if you're deleting the subscription, someone tampering with immutable storage is the least of your problems, right? Time-based retention policy is by far the recommended version when using it with Ledger. You can also do legal hold. The problem with that is at some point, someone with the right access can actually turn the immutability off. So that's why it's not recommended for this particular environment. Certainly, using immutable storage with time-based policies is the preferred way. Now, if you want to learn more about immutable storage, I would highly recommend that you go and look at the compliance assessment that was done by Cohasset and Associates, where they actually went through and actually showed how immutable storage maps beautifully onto various, mainly financial compliance requirements, and explaining exactly how it works under the hood. So you can actually, and again, this is not Microsoft saying this, right? This is not Azure saying this. This is an independent third party who came in and did a full assessment. And that's available at servicetrust.microsoft.com, along with lots of other compliance documents like GDPR and SOC 2 and FedRAMP and NIST SB 800-53 controls, all these other stuff. They're all documented up there as well. You do need to sign in though. These documents are technically NDA, but only NDA to people who have an Azure subscription. So you need to log in first, but do go ahead and look at this document. It's actually a really interesting read. If you're a bit of a nerd, but certainly from a compliance perspective, I think it's an incredibly important document. So that's Azure Ledger. Sorry, that's Ledger that's built into the Azure SQL product. So to wrap this thing up, I really want to stress a few important points here. That the team that I work on, we have a big focus on always encrypted. I didn't really talk about this. It's covered in OD32, which is Azure Active Directory for client authentication, like managed identities, and just using AAD authentication for users in general, but also Ledger. These are incredibly important technologies. All three of them are very strong technologies when you're considering zero trust, and especially the assume breach pillar of zero trust. Go ahead and kick the tires on VBS enclaves. I mean, right now it's in preview. We value your feedback here, but go ahead and just experiment with it. Create a stupid table that has one column that's a social security number or something confidential, and experiment with it. Same with Ledger. Enabling Ledger is actually incredibly simple. You literally, when you create a table, you basically with Ledger equals on, and that's essentially as well as defining where the Ledger Merkle tree is going to be stored. Do understand the pros and cons of all these controls, right? I mean, TLS is kind of pretty straightforward, but TDE is different than always encrypted. They mitigate different threats, and it's really important that you may decide to actually have both enabled at the same time. But it's really important you understand, exactly where the line is drawn between these different defenses. And finally, and I realize this is a self-serving plug, but here you go. My friends and colleagues Simona Kurtzi and Heinrich Ganzenbein and I wrote a book that came out in December last year, which goes through a lot of these. In fact, goes through all of these in gory detail, except VBS enclaves because they're brand new. Although we do talk about VBS enclaves with SQL Server on-prem because it uses VBS enclaves on-prem. It uses the hypervisor to provide isolation. But all the other stuff that we talked about is all in there as well. So if you want to sort of broaden your horizons when it comes to designing and developing secure solutions, I hope you put that on your list of books to consider. And with that, I hope you found this very useful. Again, this is a topic that's near and dear to my heart. I'm a big fan of cryptographic controls. So again, I hope it's useful, and enjoy the rest of build.